Computer. Okay. Um, Let me see if I can do this. All right, there we go. Okay, so here we are back at chapter 9, which is benzene. We learned a little bit of aromaticity Monday, and we're going to continue on with that today. And if we look at our lecture schedule here, we have 9 for the 19th and the 20th as well. We're probably going to finish up chapter 9 today. And then we have chapter 11 will start on the next one, next week on Monday. So chapter 11 is, I want to say alcohols. So, and what we'll do is we'll go back to that original format where we had the, no, we're going to start spectroscopy next time. That's right, spectroscopy. So what we'll do is we'll go to spectroscopy, and that's 2 different forms of analysis of chemical compounds so that we kind of know that we have what we have. And I'll tell you about that again starting next week. As far as after that, the following week, we're going to have our review, and our second exam is scheduled for October 28th. That'll be a top hat proctored exam as well. Okay. Any of you who are in the laboratory, you should have gotten an email today about makeup assignments and quizzes for the online stuff. Make sure you look at the email I sent on Friday. That is specifically for your section, your group. So those instructions are very specific to exactly the section you're in. Now, occasionally I move people from A and B and C sections, so ping me if that doesn't seem like you're in the right group, and we'll get that figured out. But so next week, we can, throughout the rest of this week and through Wednesday next week, any assignment you've missed, a pre-lab or a post-lab, go ahead and complete it and upload it. And upload it to the correct section on Canvas. And then I will have the quizzes, online quizzes open on Wednesday for about 6 hours so that we can, anybody who missed a quiz because they didn't know what they were supposed to do, go ahead and take that quiz. And if you've already taken it, don't worry about it. We'll start grading those things. We're still having a little trouble getting everybody in the correct slot on that thing, but we should have our grades cleared up in the next week or 2. So start looking for your grades in there. And if you don't have one, go ahead and ping your lab instructor first. And then if that doesn't resolve the situation, go ahead and call me. Okay, so as far as what is due this week, we have our homework for chapter 10, which is the one we did last time, which is amines, is due on October 16th on Friday of this Friday. The homework for chapter 9 won't be due until next week, okay? So don't worry about chapter 9, just make sure you have chapter 8 done. We're gonna have chapters 9 and 11 are both gonna be due next Friday, not this coming Friday, but the Friday after that, so that you'll have plenty of time to complete those. All right, any questions about administration before we move on to today's lecture?
So test number 2, is that going to be cumulative, or is it just going to be after what we covered after test 1?
Yes, it will be cumulative. It'll be weighted toward chapters 8 through 11. However, it will, like things like nomenclature and stuff like that and functional groups, you have to know. So, but it will focus, like over half the test is going to be on chapter 8, 9, and 10, and 11. So, but the chapters 1 through 6 will be sprinkled in there as well. Okay?
Okay, thank you.
Chemistry is unfortunately completely cumulative because once we learn about bonding, we use that bonding again in another chapter. So we kind of have to use all of those general things again and again and again. Okay. So getting back to chapter 9, we talked about benzene and how benzene was different than just having alternating single and double bonds because it follows 4 rules of aromaticity. It must be in a ring, must have a p orbital available on each of the atoms in the ring, it must have the correct number of electrons, 2, 6, 10, and it must do something else. It must be planar, it must be flat. So all of those orbitals can overlap evenly. Once we satisfy all those rules, we can, not even have to have carbon. We can have oxygen, we can have nitrogen. Anything with an available p orbital can be done in those systems. Then we learned about how, because the rings on these aromatic systems are so electron rich, the only reaction we do with them is called electrophilic aromatic substitution. Okay, because the electrons on the top of the ring, those are the ones that are actually going to, the positive charge is going to come attack those electrons. And then the reason it's substitute is because that aromaticity saves so much energy it wants to re-aromatize. Okay, so what we'll see in every single step is, every single one of these mechanisms is that we have a ring that's electron rich. It reaches out and grabs something that is electron poor, has a positive charge, and then it's going to stabilize that positive charge on the ring for a little while, but then it's going to want to spit a proton out to re-aromatize. Okay, so those are the three steps in the mechanism. No matter what we're trying to substitute it with, those are the three things that are going to happen. Okay, so let me share my slides, and we're going to talk about direction. I showed you last time that we had a collection of different groups, and they were ortho and para, or they were meta directing. Okay, so in the ortho and para, that means that they would be right next to the substituent or opposite the substituent in the number 4 position. And those actually are both together. The ortho and para are both activating, and you can have the substitution at either one of those sites in the reaction. And I'm going to show you why. The other ones were meta directing, meaning the meta, it was only going to be in the 1, 2, 3 position, the 1, 3 position, and those were directing that way. And we saw that the ortho para directors all had lone pairs or a very nonpolar bond. And all of the meta directors had electron withdrawing groups like carbonyls or something with a partially positive or positive charge on them. Okay, now we're going to use those simple analysis of the ortho-para director versus the meta director to decide why these do it. And so we're going to run through each of the steps of the mechanism with each of these different groups and show you why it's going to be one way or the other. Okay, so in general, oops, got to let somebody in here in the waiting room. Okay, so in general, the rate of these electrophilic aromatic substitution reactions are determined by the slowest step. Okay, so typically, making the electrophile is not the slowest step. That usually happens fairly quickly because it's an acid-base reaction, whatever you have plus a Lewis acid. And that happens really quickly. The slow step is almost always the attack of the electrophile on the aromatic ring to give that resonance stabilized cation intermediate. Okay. Now, the more stable that intermediate is, the more likely that reaction is going to happen, and it's going to happen faster. Okay. So if we can stabilize that positive charge on the ring for a limited amount of time, then we can have that reaction go faster. Okay. So that being said, we want to see that most ortho-para directors, the ortho-para attack forms the more stable cation than the meta, and that means the ortho-para products form faster than the meta products. Doesn't mean you aren't going to form meta products. It's directed toward and mostly that, but occasionally you do have some of the other. For the meta directors, what we're looking for is that once it attacks meta, it forms the more stable cation than if you attacked ortho and para, and therefore the meta products are formed faster than the ortho para. So we have to think about stability and what makes stability, okay? So in the case of benzene rings, and we saw this on some other things, conjugation or the resonance structures, having one or more resonance structures helps stabilize charge over multiple atoms. If you can use that resonance form, like drawing multiple different Lewis dot structures that all are equivalent, the more of those you can do, the more stable that intermediate will be. Okay, so let's take a look at this in a little bit deeper. Okay, so let's start with this methoxy group here. It's a methyl and an oxygen. And when we have that on a benzene ring, that has a special name, anisole. Okay, so if we have this compound right here, the first thing we need to think about is, okay, anisole has a lone pair here and here, here and here. Sorry. It has lone pairs on it. So In theory, it should be ortho pair directing and it should be activating because of those lone pairs. That's what we saw on the table last time. Okay. Now let's prove it to ourselves why that's true. Okay. So the first step in our reaction, of course, is the formation of that electrophile. And we've already done that for us here. So we've made our NO2 plus. And so that is our electrophile. And so the next thing that's going to happen is we're going to use the electrons from the pi bond over here to reach out and grab that to form our new bond. Okay. When we do that, assuming it attacks at this meta position, so we have this nitro. Okay, remember meta is 1, 3. So that's the 1, 3 position here. Assuming we did that, we would form a positive charge immediately on the carbon, the other carbon that had that double bond on it, because it now has less electrons because of the new sigma bond. Okay. But by resonance, we can actually just flip these electrons over and move the positive charge to this position. And we can do that again to move the positive charge over to this position. Notice that these can continue to keep rolling around again and again and again. And therefore, we have 3 possible resonance structures that will stabilize that positive charge. Okay. Now, once we have these 3 stable things that can happen, the next thing that can happen is we can have a base come in and pull off our hydrogen and generate move the electrons down here to re-aromatize. And that's our last step. That's our 3rd step. Okay, but the point is we have 3 different equivalent resonance structures that stabilize that charge, okay, to give us that meta attack. So that was if we attacked meta. What if we attacked somewhere else? Okay, let's attack ortho or para. And we're going to start with para, and I'll show you it's almost the same. So instead of doing meta, where it ends up on this carbon here, we're going to actually end it up in the para, the 4 position here. And let's look at what we see. Okay, so the first thing, of course, because we're pulling these electrons off, that's where our first positive charge is going to be. Here, I'm going to blow this up. Okay, so because we've taken these electrons from here, but we're taking them and attaching them to the nitrogen on there, that's going to leave this our positive charge, our first positive charge. Okay, so okay, that looks exactly like the other thing, right? We had a positive charge available to us. However, when we do that, we can also, by resonance, move that positive charge to this carbon. Okay, that's pretty similar. That's what we saw before. But wait a minute, we have a lone pair up here. We can move that lone pair down here, and so the positive charge is now also on an oxygen. We did not see that in the previous structure. We did not have a positive charge available to us by resonance in the meta attack. And so if we had the electrons up there, well, let's give those electrons, excuse me. Let's give the electrons back to the benzene ring. And when we do that, we have our positive charge right next to our hydrogen and our NO2 group here. This is NO2. And our last fast step would be, of course, a base reacting with this, pulling it off, giving those sigma bond electrons back to the aromatic ring, giving us our final structure. Okay, so the difference in this para attack versus the ortho attack is that you have a 4th resonance structure. Okay, so anytime the more resonance structures you have, the more stable that structure is. So this one having 4 resonance structures means that this is the more stable intermediate. Excuse me. And if this is the more stable intermediate, then it will react faster. Okay. So in this case here, having that methoxy group there allows us a 4th resonance structure, which means that the para substitution is faster than the meta substitution. Only para has 4 resonance structures. Ah, good question. I have a question in the chat. Is para the only? Actually, it turns out ortho is going to give us the same 4 resonance structures. We're just going to show them in a different place. In fact, I'm going to go ahead and draw the 4 resonance structures for the ortho right here now. Okay, so what we're going to see is if instead of going to this number 4 position, let's go to this number 2 position. That's the ortho position, right? So our first structure is going to look like this. And then we have NO2 and a hydrogen here. And we have our OMe here. And when we do that, we have a positive charge here. We have a double bond there and a double bond there. Okay. So we now have our first resonance structure. But what we can do is we can do the exact same thing we did with the other ones and move that around the ring. So the next one that we can do is we can move it. Let's move these electrons over here. I'm sorry. Yeah, let's move. Let's move these electrons over here. Yeah, those are too far away. We need to move. If we move these electrons over to, there we go, these electrons over here to balance that charge right there, our next resonance structure is going to give us our positive charge here and our NO2, our hydrogen here, our OMe here, and our double bond there. Okay, so our positive charge is here on this one, it's there on that one. So that's looking similar to this structure here on our other one. Then we can move these electrons down here to give us our positive charge on that next atom. And that's going to look like this positive charge here, NO2, H, double bond, and then OMe. So see how that positive charge is moved around the ring. And now what we can do is we can now take those electrons on that oxygen and move those down into the ring and put the positive charge on our oxygen, just like we did before. And so I'll draw that right here. So we now have all of those. Sorry, I don't have a double bond there. And we have a double bond going to that oxygen and a positive charge on the oxygen. The methyl group's still here. We have the hydrogen and the nitro group. So even when we get on that 2 position or the ortho position, we still have 4 resonance structures available to us. And the 4 resonance structures are going to be faster than the 3 resonance structures. However, what's the problem with this? We start to run into trouble when this group gets big. That ortho position is going to start to be blocked because of sterics. Okay, so while it is an ortho para director, if this is small, you're going to see both ortho and para products. If this group right here starts getting really big, we're going to start to see more para products than ortho products. But both ortho attack and para attack give rise to 4 resonance structures, making it faster than the meta attack, which only has 3 resonance structures. Okay, does that make sense? Okay, so in this case, we've shown that because we have that lone pair on oxygen here, that lone pair on oxygen gives us our 4th stabilized charge, and it has the charge off of the ring. Okay, so that means that's why it's an ortho para director. Okay, so let's go to something that is a meta director. Okay, so let's see if that same argument holds for a meta direction that we have. Okay, so when we do our nitro, the one thing I want to draw attention to is if we draw out our Lewis dot structure for our nitro group here, we have a positive charge on nitrogen and a negative charge on oxygen. So our Lewis dot structure shows that we have a nitrogen with a positive charge, but the positive and charge cancel out, so the net molecular charge is 0. But I want to show you that this Lewis dot structure that we drew in chapter 1 and 2 is where that there's a positive charge on that nitrogen. So let's go ahead and do our reaction, and we're going to do it first with a meta attack because we did meta attack first last time. Let's do it again. And if we do meta attack, we, of course, the first thing we do is form our electrophile. That's the fast step. Now the next step has these electrons reaching out to grab that nitro group there and give us our first positive charge. Okay, so that's our first positive charge. That looks pretty similar to the one in the last one. And by just moving these electrons over, we'll get the positive charge to move to here. So here's our first positive charge, it moves there. And moving the electrons again gives our positive charge there. So if we have this meta attack, we have 3 resonance structures. Okay, not 4, but 3 is pretty good. Okay, and then of course the last step is that loss of hydrogen. So this is not bad. Okay, we have fewer resonance structures, so it's slower than the orthopara director, right? Because it only has 3 resonance structures. But it's still, you know, pretty okay and pretty valid because the positive charge is still resonance stabilized. So that's okay. I don't have a problem with that. That makes sense, right? So let's try to do it in the para attack and see if it changes anything. Okay. So let's do that same thing. And instead of going with that meta attack, we're going to go to the para attack, which puts our first positive charge next to it right here. And then when we try to move the electrons to here, we now have a positive charge in that position right next to that nitrogen, okay? But then we can move it around to the other one right here. Okay. What's the problem with having that positive charge on the nitrogen? Okay. The problem with that is that now we have a positive charge in the ring and a nitrogen with a positive charge, and then an oxygen with a negative charge here. We have 2 positive charges right next to each other. Those 2 positive charges want to repel each other. So that's not a contributor. That is a very disfavored contributor because you have 2 positive charges right next to each other, which means this one is actually a very limited, if at all, contributor to the system. That means that para attack here only has 2 resonance contributors. Not 3 that the meta had, but 2. And if it has 2 resonance contributors, that makes it even slower reaction. So we might see a little bit of it, but it's really, really slow. Okay. So now do we see the argument on why orthopara directors are #1 activating, because they have 4 resonance stabilized characters. #2, why they're faster, and why they direct orthopara, because in that orthopara, they get that 4th resonance state. Now, if they do get attacked meta, which happens slower, it only has 3 resonance states. Now, in the case of an electronic drawing group or a meta director, remember those are all deactivators with positive or partially positive charges, we end up getting a positive or partially positive charge at this position, no matter what you do, and you eliminate one of the resonance contributors, slowing the reaction down even more, making it drive back to maybe starting materials and go back to the meta attack. Okay? So this is why we want to look at that chart, and now we know 2 things from that chart. Those lone pairs make it faster and make it orthopara. Positive charges or partially positive charges make it meta direction and deactivates it. All right, questions on how this works? Okay. All right, so the net result here is that anything that can delocalize that positive charge or have these electrons lowers that activation energy and activates the system, okay? Any resonance or inductive effects that give a positive charge to the system, like the nitro group or this carbonyl, which is partially positive. The sulfur has a positive charge on it. This nitrogen has a positive charge on it, and this is inductively. Remember, those chlorines are pulling electron density away, so it's partially positive. Decreases the electron on the ring and therefore deactivates the ring to further electrophilic aromatic substitution. Okay, so now halogens are one of those weird ones, right? That was at the intermediate scale. It's an orthopara director, but it's a mild deactivator. Okay. Now, I want to talk about them specifically because they're right at the bridge point. They're still orthopara, but they're the first thing that we call a deactivator. Now, by inductive effects, meaning that it is more electronegative than carbon, it's trying to pull electrons away from the carbon, therefore reducing the activation effect. It's pulling electrons away. However, because it has lone pairs, by resonance effect, it can direct orthopara. So inductively, it's slowing the reaction down because of electronic drawing. However, those lone pairs allow it to contribute to that orthopara stabilization of a fourth resonance contributor to the orthopara direction. So that's why halogens are that weird thing that's right in the middle where it's slightly deactivating. However, it is also very much an orthopara director. 28. Okay. So now let's take a special look at the phenols. Okay. Phenol is one of those weird ones that we have. We can't actually make it directly with like using hydroxide as a displacing agent. It's not strong enough. But we have some cool things that we can do with it. So basically it's an alcohol, but it's bound to this benzene ring. And so we call it phenyl alcohol or phenol. Now, when you have multiple things attached to this, they actually have different names. And some of the common names are things that, like with this methyl group on here, okay, you would want to call this like toluene hydroxy, right? But actually, alkyl groups are lower priority than alcohols, therefore it's named for the alcohol, so it's phenol, and so it's methylphenol. But it has a common name, and it's called creosol, okay? You may have heard that name if you've ever bought railroad ties or been telephone poles, saying, oh, this is creosol-soaked material. That is a petroleum byproduct that has a whole bunch of these phenolic compounds, which are antioxidants, not great for our that are antioxidants that can be used to inhibit rot in wood. And so these are actually used extensively in that kind of system here. However, just like in the case of diols, triols, and tetraols, we have different names for the dihydroxybenzenes. The pure name is going to be the 1,2-benzene diol, because we're naming it as a diol, 1,3-diol or 1,4-diol. However, they have special names. The 1,2 is called catechol, okay? And so it's as all at the end, so it's an alcohol, and it's called catechol. And this is special because you can imagine these two things can react with the same thing at the same time and make a ring. So it's called catechol. The next one is the meta derivative here, and we call that resorcinol. Okay, and then this one is the para derivative, and we call this hydroquinone. Okay, so but the IUPAC names would be the benzene diols, the 1, 2, 1, 3, and 1, 4. Okay, so if this is kind of like an alcohol, but not quite an alcohol because the electron contributing, what can we also do with it? Okay. So one of the cool things is that these phenols are very biologically active. And that hydrogen bonding that are available to that with that alcohol allows it to be used in the body in a bunch of different ways. So one of the ways that we can think about this is that this simple compound right here, just a methyl group and an isopropyl group with this alcohol making it a little bit water soluble, it actually is a biologically active system called thymol. Okay. Now, one of the other cool things is the flavor that actually makes vanilla is actually controlled by this benzaldehyde group here, but it has a phenolic group on it and a methoxy group on it. So this was a diol, and then they stuck a methyl group here, and it allows it to have, it's number one, volatile and can be sensed by the body as the smell vanilla. Okay. Now here is another one that is used in biological systems. Again, it uses this 1,3-diol system, so we call that resorcinol. but it has this hexyl group on here. And so this also is used in biological systems. It's quite an odd odor. And so that's what it's commonly, that's how it was isolated because of the odd odor. We also have another odd smelling beast here, eugenol. And so it's also, and then this is actually processed by the liver and the body. And it has this long aliphatic chain, which makes it very fatty soluble, but it still does a lot of the chemistry of phenols. Okay, so if we think about phenols as kind of like alcohols, that's true. However, you have to think about that there's this large pool of electron density in the benzene ring. Okay, so that's going to change the acidity of the system. Now, the idea here is when we have this, when we looked at acidity of compounds like this, we saw that if we could delocalize that negative charge, spread it out over a number of atoms, that makes it more acidic, okay? So for example, if we have acetic acid is more acidic than ethanol because we can spread that negative charge out over two spaces here, okay? We have that same opportunity available to us in the phenols where, while it doesn't directly, it can inductively share this negative charge around this ring, making it more acidic than a standard alcohol, but less acidic than our acetic acid. So we can actually use that difference in acidity to do some really creative work in the fact that we can make them water soluble or water insoluble by changing the pH. Okay, so like I said before, the greater acidity of the phenols compared to the alcohol has everything to do with the ability to spread that charge out, okay? And just like in the electrophilic substitution reactions, where we use the lone pair on that oxygen to create a double bond with the ring, we can do that same kind of thing to give a resonance contributor. So if we want to just keep the charge on the oxygen, we still have two different resonance structures available to us right here. Just by calculating, those are fairly equivalent. However, if we move electrons from that oxygen down into the ring, we can actually move that negative charge all the way around the ring and then back up onto that oxygen. Well, it doesn't spend a whole bunch of time along the ring because it's electron rich. It spends enough time on the electron ring to increase the acidity of phenol compared with an alcohol, which has to have that negative charge only on the oxygen. Okay, so if putting a negative charge on the ring makes phenol more acidic than regular alcohols, can we make phenols more or less acidic by changing the ring? And the answer is yes, okay? So anytime you have an electron withdrawing group on a system, either inductively or directly, you can increase the acidity of your phenol. So without any groups on there at all we have is hydrogens on this end right here. We have a pKa of 9.95, so around 10. Just by adding the inductive effect of a single chlorine here, we can drop that about 0.75 in the pKa, making it more acidic, okay? By adding a true electron withdrawing group with that positive charge here, remember this nitrogen has that positive charge here, that means we can stabilize having that negative charge right here on that ring. We have a negative and a positive together. That makes it even more acidic, dropping it all the way down to 7.15, okay? So that's the inductive effect helping us to, so the resonance effect is just spreading it on the ring, but the inductive effect of a group attached, and notice it's best if it's attached para or ortho to the system, because that's where we're going to get our negative charge showing up. So anytime you have it in those positions, it's even going to enhance the acidity of our system. But just the inductive effect is enough to increase the acidity alone. Okay, so how can we use this to our advantage? Well, we can use this to our advantage because they are more acidic than alcohols, we can deprotonate them with weaker bases. So for example, phenol right here is, in this case, the stronger acid. We use a very strong base, and we can pull that proton off and make it into a salt, okay? So this is what we call sodium phenoxide. So it's phenol, but it's the anion right here. And then we can create water from that, okay? So in this case here, our sodium phenoxide and our water are the weaker acids and bases. Therefore, the equilibrium lies in the direction of the phenoxide. However, if we use a weaker base, for example, in this case, sodium bicarbonate, we can do a partial deprotonation, but we'd end up making carbonic acid, which is more acidic than the phenol is. And therefore, while we can make some of this material, the equilibrium actually lies toward the phenol, not to the phenoxide. Okay, so that being said, now that we know that the phenol is much more acidic than an alcohol, we can take that to our advantage to separate them from a mixture of things that are almost the same, but we can use that acidity. So if you can imagine, we did the experiment with the acids and bases. So if you made the solution that was just the right acidity or basicity, you would get one of them to dissolve and the other one would not. So let's do that experiment here. So we have this cyclohexanol, which has a pK of around 16. We have this, which is a pK around 10, okay? And then we know that if we can, both of these dissolve in ether, and we know that we can fully deprotonate this phenol using sodium hydroxide to get it completely to the phenoxide. Once it's pulled, once it's deprotonated, made into the phenoxide, it is water soluble, okay? Notice this has 6 carbons on it, so this is water insoluble, this is water insoluble as well, until it is deprotonated. Now, if we took that and separated out, the alcohol which wasn't deprotonated stays in the non-water layer, okay? And therefore we can just take the ether off that and we can separate out our cyclohexanol. However, the phenol has been dissolved in the water as the phenoxide, which means it's in the water layer. But to regenerate the phenol, we have to acidify it. And once we acidify it, it actually comes out of solution as a liquid. And we now have our alcohol and our phenol separated by a simple process of knowing exactly that you can deprotonate one with this base, but you cannot deprotonate the other, giving us a clean separation of that system. So that's the demonstration of how the phenols are more acidic than regular aliphatic alcohols. Okay. So you might have heard of the term antioxidant, okay? Antioxidant is not only used in a biological sense, but it's also used as a preservative for many different things in chemical reactions, in fuels, in products we use in our house. And so the idea here is that phenols, and both that and hydroquinone in particular, slowly oxidize in air. And when they slowly oxidize in air, they go to peroxides. And when they do that, they can be, they basically, those peroxides can go on to react other things. And the peroxides, if you concentrate on them, are very explosive. Okay. So in the case of stuff that has double bonds or like ethers and certain chemicals, we have like acrylics, which is a vinyl group with a carboxylic acid ester on it. Those things are very reactive toward oxygen. They will react with oxygen to form these peroxides, okay? Now, the idea is that the phenols, if you add them to the system, the phenol is going to oxidize first, making it not form those peroxides, not form those reactants with oxygen, okay? So in the case of, we're actually using them as radical. So if you actually accidentally formed a peroxide in the system and you reacted it with something with a double bond, you would end up forming radicals, okay? And those radicals would go on and continue to react and react and react. And so what can happen with this particular system is they just keep reacting, and you can imagine you have a liquid, and if it keeps reacting to make these radicals, it'll create a gel, and then it'll create a solid, and then it'll mess up your chemical. You can't use it for anything. Okay. And it all has to do with the idea that these radicals keep adding across other double bonds and other double bonds and other double bonds until it's all stitched together. And we'll talk a little bit more about that chain reaction when we talk about polymers in chapter 16. Okay. But the idea here is that you can actually use phenols to inhibit this oxygen diradical reaction such that it doesn't form these, and we can inhibit that reaction. Now, that would do it well in a chemical sense, but we can also use these as antioxidants in a biological sense. So for example, we have one of those antioxidants that are found in the stores is vitamin E. And vitamin E is a fat-soluble chain that has a phenol on it. And this is the active part right here. That phenol is the one that interacts with the biological systems to decrease unwanted radical reactions within a biological system. Okay, so the phenol here is the one that absorbs that oxidizer in the system and does not allow it to react with other biological molecules of interest. Now, there's also some synthetic versions of this, like BHT, which is butylated hydroxytoluene. And so basically we have two T-butyl groups here, and this is toluene right here. And so in this case here, we use those big groups to make it fat soluble, and so we can actually use these as a preservative in food and in odorants and chemicals we use around the house. And another version of that is this one right here. It's similar to it right here, but it has this oxygen here, which actually makes this a better antioxidant than this one because it makes this slightly less acidic, and it can be used in a number of different systems. But again, both of these are fat-soluble, non-water soluble systems. Okay. So questions on, benzene and its derivatives, why it works, aromaticity, orthoparadirecting. We only have one mechanism, so that's great. Any questions on benzene and benzene derivatives? Okay. So I have an opportunity here to either pause and start with chapter 11 on Monday, or we can start chapter 11 with the goals specifically related to IR spectroscopy. Any votes either way? Okay. So what I'm going to do is I'm going to go ahead and start chapter 11, goal 1, and this is talking about IR spectroscopy. Okay. So again, these things are posted on Tracks. The full slides are on Tracks, Canvas, and the goal slides are on Top Hat. Okay, so in spectroscopy, we have 3 different spectroscopic techniques we're going to talk about in this chapter. The first one is IR spectroscopy, which is infrared spectroscopy. The second one is proton spectroscopy, NMR, which is nuclear magnetic resonance spectroscopy. So we're going to talk about just hydrogens with just one proton in them. That's what the 1 stands for. It's the isotope. And then we're also going to talk about carbon-13. Carbon-13 is actually an unusual isotope of carbon. We'll talk about how to use it to measure where things are in this. So the key thing that we need to remember here is that IR spectroscopy is a heat and vibration-based spectroscopy. So what we're seeing there is we're looking at bonds and functional groups. Okay. In NMR spectroscopy, we're actually looking at connections, where the different hydrogens, how close hydrogens are to each other, and whether or not they're equivalent. And in carbon-13, we can actually say this carbon's attached to this carbon's attached to this carbon. Okay. So the three different techniques tell us three different things. And by adding all three together, we can get a good, reliable method for identifying any organic compound. Okay. So the first one is IR spectroscopy. Okay. So let's refresh ourselves about what light is. Light is electromagnetic radiation. So as light moves along in a wave and a particle here, it has a vector component, an electrical component, and a magnetic component. Okay. So the magnetic component goes this way, the electrical component that way, and its direction goes in this direction. Okay. So that means that there's a magnetic component that can interact with certain things, like the nucleus of an atom. And there is also this electronic component that can react with other things. But it can also be used in that way. And so if you can imagine, you can get something to oscillate at the same frequency as the light, it will start absorbing that light and oscillating. And that's where IR spectroscopy comes in. Okay, so the idea is that electromagnetic radiation is all light, from very long wavelengths to very short wavelengths. Okay, the wavelength is literally the distance between the top of one curve to the top of the next curve. You can pick any point you want, but it's from that same location on each wave. And these wavelengths can be as long as kilometers, 3 kilometers from wave to wave. That's how long it takes. And sometimes they can be picometers, which is 10 to the minus 9. Right? So it's like really, really small. Okay, so, but that's sometimes hard to think about. So we think about frequency. Frequency is basically the number of waves that can happen in 1 second. So that's directly related, directly proportional to the wavelength. So if this took a mile and it was moving at 1 second, you have a frequency of 1. But if this one is picometers, then you have millions of these in that 1 second. So that's where wavelength and frequency are interrelated. Okay. But to make things easier to talk about, we use the term hertz. Hertz means per second, which is number of frequency per second. Okay, so that's the notation we're going to be using there. Now, in IR, we're going to look at another way to look at this is per centimeter, or a CM to the minus 1, which is wave number. Okay, so I said before that these wavelengths go from kilometers long to very small things. And so if we look at this, this is like long radio waves over here. This is like 3 kilometers long, okay, right here. And so those long radio waves are used in a bunch of different ways. In fact, we use stuff over here in NMR because it interacts with the nucleus of atoms because of a magnetic component. And then, of course, we know about microwaves. Microwaves can interact with certain bond frequencies that we have. For example, the bond between hydrogen and oxygen, specifically in water. Okay, you can use microwaves, 2.54 gigahertz. And what that does is that excites that molecule and it generates heat. That's why microwaves heat things, and only things with water in them work well in the microwave. Okay. The next zone we're going to talk about is IR. This is where we're actually vibrating different functional groups. Then there's also UV. In UV, we can actually see how many double bonds are linked together. And then we get up to bigger things like X-rays and gamma rays, which we can also use for spectroscopy, but not in this class. Okay, so the most important thing for us is this infrared, which is just below visible light. Okay, so in general, we're talking about the wavelength that extends from 2.5 to 10 to the minus 6 meters to 2.5 10 to the minus 5 meters, okay? Now, because it's difficult to do the minus 6 and the minus 5, we've actually converted this into reciprocal centimeters, or per centimeter, vibrations per centimeter, because it gives us a nice consistent range, okay? So when we convert things to wave numbers, our range only goes from 4,000 reciprocal centimeters, or wave numbers, to 400 reciprocal centimeters, or wave numbers. So the good thing about this is that gives us a nice, easier number to play with. So we just need to remember ranges from 4,000 to 400. Okay. And there's the conversion from one to the other. But the most important thing is that the wave numbers are equated to energy. Okay. So if you remember nothing else about IR spectroscopy, remember this table. Okay. So in this table, let's see, we go to 2, right? Yeah. Okay. We have increasing wave numbers going from 400 to 4,000, but it's also increasing energy. Okay, that's the key here, energy. Okay, so what does that mean? Okay, if we look at different functional groups and different types of bonds, it takes a different amount of energy to have them vibrate. Okay, so the stronger the bond, the higher energy you need to absorb that and make it vibrate. The weaker the bond, the less energy you need to do that. Okay, but then we have other things that contribute to that. And what we call those is the light atom high frequencies. Okay. So what we're going to see here is we're going to use this chart here, and we have 4 zones of interest. Okay, we have things bonded to hydrogen in this 2,500 to 4,000 range. Okay, in this 2,500 to 2,000 range, we have triple bonds. We have 2 different functional groups that show up there. That is the alkyne and the nitrile. The next zone is 2,000 to 1,500. That's where we're going to see all our carbonyls, all our carbon-carbon double bonds, and all our carbon-nitrogen double bonds. Okay, and then below 1,500 is where we see all our single bonds. Okay, so think about it. Single bond is easier to vibrate because it's not held as tightly. By the time you get a double bond, that's 2 bonds holding it together. It needs more energy to vibrate. By the time you get a third double bond in there, you need even more energy to vibrate. Okay, but this is a higher frequency because you have a heavy atom and a light atom, and that heavy atom and light atom vibrates even faster. Okay, so look at it as a function of heavy atom, light atom, and bond strength, and then you should be able to rack and stack any functional group in this range. Okay, so let's look at them independently. So what would an infrared spectrum look like? So in general, it looks something like this, where we usually have 4,000 on one end, right here, wave numbers, and we have 400 somewhere on the other end. That's the usual range we see these things at. Okay. And then we have, usually it's done as a function of percent transmittance. What that means is that these wavelengths here went straight through the sample. Didn't get absorbed. There was no functional group that could absorb that energy. So it just went straight through the sample. Now, there's some functional group here that's absorbing that energy. And if it's absorbing that energy, it doesn't go through the sample, it gets absorbed, and so the percent transmittance goes down. And then you have another region where, oh, nothing's absorbing that energy. So that's what we're seeing in the spectrum is no absorption, some absorption, a little bit of absorption, no absorption. Then look how we can get really strong peaks right over here as we go further and further out. So this is the typical kind of spectrum you'll see. And what you'll be able to identify is not what's missing necessarily, but what absorbs very strongly. So when something starts absorbing strongly, you know that type of bond is there. And if you know that type of bond is there, you can help narrow down what functional group you have. So IR is great for determining functional groups. Not necessarily the exact conformation of something, but definitely functional groups. Okay, so let's talk about the different molecular vibrations and where they appear. Okay, so if we start at the top end of the range, right here, nothing really absorbs at 4,000. But the first thing we see absorbing is this oxygen, hydrogen, OH. So it's basically the alcohol group. Okay. So in the case of an alcohol group, we have it at that 3,500 to 4,000. It's a very strong bond because we know this bond absorbs a lot of energy, and so it's very strong. However, it's really broad. And the way we think about that is because it can hydrogen bond, it's going to broaden out that peak. So there's one where it's hydrogen bonded to one thing, it's hydrogen bonded to 2 things, it's hydrogen bonded to 3 things. Those all have different energies, and therefore it gives us a broader peak. However, if we have that OH next to a carbonyl to make it a carboxylic acid, it shifts it down. Okay? It's still broad and it's still strong, but it shifts it down in energy. Now, the next most likely group there is so we have oxygen, we go to nitrogen. We also see absorption in that range where we have the nitrogen, hydrogen bond, or the amines, and that has a medium strength peak. And then we have two different types of carbons that are above 3,000, and then we have one type of carbon below 3,000. And what the key thing to remember here is that the sp hybridized is the alkyne is the highest in energy. The sp2 is the intermediate in energy, and the sp3 is the lowest in this set of carbon hydrogen bonds. Okay, so you can tell by where these show up whether it's sp3 or an alkane, sp2 an alkene, sp3 an alkyne, just by following where those hydrogens are around this 3,000 model. Okay. Now, so that gives us all of our light atom high frequency vibrations. Okay, so it's oxygen, hydrogen, nitrogen, hydrogen, and carbon. Now we're going to move on to triple bonds. Okay, and as you'd think that they absorb the highest of the set in double bonds and triple bond, but it's very weak. Okay, it's weak because it's very, number one, this is not a very polar bond. So it's hard to absorb the energy, but it's going to be the highest carbon-carbon bond we see is that carbon-carbon triple bond, the highest in energy. And then next we go down to the double bonds. Carbonyls and alkenes are next. And the carbonyls in particular, because they're polar bond, they're very strong, partially positive, partially negative. The alkene is not necessarily as polar bond and therefore is a weaker bond. And then once we go to the singles like this, the carbon-oxygen single bond, this is again a polar bond and we see a strong absorption. So the more polar the bond, the stronger the absorption intensity will be. Okay, so what does that look like in a spectrum? Okay, so just looking at this portion right here, we see that we have, number one, a sharp peak above 3,000 here. So this is probably a CH peak and probably an alkyne because it's so high up. We have these peaks below here, which tells us we have an sp3 or an alkane peak somewhere here. And we also see at 2200 right here, our carbon-carbon stretch. Notice this is smaller. This is less than half of the absorption right here. This is our 50% mark. So anything over 50% is considered strong. Anything at 50% is medium, and anything less than about 25% is what we call weak. Okay. But it has to be strong enough that we see it away from baseline, or away from what's not absorbing. Okay, so now we have 4 different zones to deal with. We have things with hydrogen, which are in the highest end. And we can tell the difference between whether it's bonded to oxygen or bonded to nitrogen. And we can tell the difference between it's bonded to different types of carbon. The next zone we have is our strongest triple bonds. Then we have our double bonds. And because of polarity, we should be able to tell whether they're going to be strong, medium, or weak. And then we have our single bonds right here, which again are going to be weak. The less polar they are, they're going to be stronger the more polar they are. And then as our polarity drops, we change our strength again. Okay, so questions on the zones. Just seeing those zones is helpful enough that you should be able to pick out where peaks should be. Okay, I'll go ahead and use the chat if you don't want to unmute you. So let's talk about different kind of functional groups and what their spectra would look like, okay? So just the idea that we have an alkane, We're expecting that to be an sp3 hybridized carbon, so we expect that stretch to be just below 3,000, and that should be the only thing we see. We have a carbon-carbon single bond, we have carbon hydrogens. That's all we have in our spectrum right here. So what we see is our first strongest bond here is our carbon hydrogen stretch. And notice it's right here between 28 and 3,000, and it's really kind of strong because, you know, carbon hydrogen, it's not that polar bond, but there's a whole bunch of those carbon hydrogens there. Then the only other thing we see is below 1,500. So I'm assuming these are carbon-carbon bonds over here because it's below 1,500, and so that's where we should see single bonds, and they're not very strong, suggesting that maybe they're not a very polar molecule. Okay. Notice that's about all we see, and then this is probably some kind of carbon-carbon bend or something. Okay. So alkanes should only show hydrogens between 3,000 and 2,800, and maybe something below 1,500. Notice the rest of that area is completely blank. That's where all of our other functional groups kind of show up. So that's kind of cool. Okay, let's go from something simple like an alkane to changing the hybridization on carbon. And we're going to go to an alkene. So now, in theory, we should change where that carbon hydrogen stretch is, because now it should be above 3,000. And we should also see our carbon-carbon double bond stretch as well. So what we see when we pull up the spectrum here is we have, this is our 3,000 peak. So we have the sp2 hybridized hydrogens above 3,000, and then our regular aliphatic hydrogens below 3,000. But at 1,600 here, we have our carbon-carbon double bond. Okay. And everything else down below here are going to be carbon-carbon single bonds because it's below 1,500. So we can tell the difference between an alkane and an alkene because of this peak here and this peak here are those two new peaks, the carbon-carbon double bond peak and the sp2 hybridized peak. All right, so let's go ahead and make it into a triple bond, okay? We'll still have some aliphatic there, so we'll see that that hasn't moved. And so we have the hydrogen for our alkyne, again, nice sharp peak, but it's right here at 3,300. So it's well above where the alkene peak is, as well as being above where the alkane peaks are. But notice we lose that peak at 1,600, which is where the alkene peak was, and we gain our new peak at 2,200. I'm sorry, 2,100. So that we now know we've changed from an alkene to an alkyne, and then everything else is below 1,500. So that's the only functional groups we have available to us. So going from, so now we can tell the difference between hydrocarbons. Alkanes, alkenes, alkynes, because they show up in different places, they'll shift around a little bit. So what happens when you add an alcohol to something, okay? Well, what we're gonna see is we're gonna see what we call a big, broad peak. And remember, it's an oxygen hydrogen, so that's a light atom, heavy atom, which means it's gonna be above 3,000. So let's pull that section up. So above 3,000 here, this is 3,000 here, and we apparently have an aliphatic alcohol because we only have the sp3 hybridized hydrogens here, but we have this big, broad peak. Okay, so this is indicative of alcohol peaks. Okay, carboxylic acid peaks looks a little bit different, and I'll show you that in a minute. But if we go over to this side of here, we again have nothing above 1,500. We have a carbon-carbon, carbon-carbon single bond, and we have a carbon-oxygen single bond, and that's all we see in our spectrum. And so that's just this nice little fentanyl right here. Okay, so that's just by changing from an alkane to an alcohol, we get this nice big peak to tell us we've changed functional groups. Okay, and what if we want to keep that carbon-oxygen bond but get rid of that hydrogen by making it an ether? So now we have a carbon oxygen-carbon peak. So we've taken away that light atom, that hydrogen-oxygen absorption, and so we have nothing above 3,000. We still have our sp3 hybridized carbon-hydrogen bonds here. We have nothing above 1,500, and we now have our carbon-oxygen peak below 1,500. Okay, so we can easily tell when we've made an ether from an alcohol, or we've made an alcohol from an ether, for looking for the big peak in this 3,000, 3,300 range. Okay, so let's look at another functional group. Okay, so interesting enough, as you change functional groups, the spectrums change. And so that's the cool thing about IR, is you can immediately start recognizing functional groups. Okay, now nitrogen has something kind of interesting about it. So in the case of an alcohol, you have one hydrogen, and they are, oh, good question. I have a question in the chat room about, do we need to memorize ranges? The range from 4,000 to the 3,000, you need to know what's in that range. You need to know what's in that 3,000 to 2,800 range. You need to know that those are the sp3 hybridized carbon. You need to know where the triple bonds show up, where the double bonds show up, and know that everything else falls below that. So if you have to remember the atoms with hydrogens on them, triple bonds, double bonds. And then you just assume everything else is below that 1,500 bond. Okay, does that answer your question? So again, if you just use that table, know where all those little marks on where the functional groups fall in that table, that's a great place to start. Okay, so nitrogen has something interesting to it in the fact that nitrogen has a possibility of having, if we have an R group here, because it is tetrahedral because of its sp3 hybridization, it has, when it's primary, and it only has one R group on it, it has two hydrogens, but they're not equivalent. They actually have different stretches. And because they have different stretches, you actually see two peaks in that high energy range above 3,000. So for primary amines, you see two peaks here, because each of those hydrogens has its own little vibration. If you then replace one of these hydrogens with another R group and have a second one, you end up having one peak here. And if you replace that last hydrogen, you no longer have a hydrogen-nitrogen bond, and therefore you have nothing in there. Just like when we went from an alcohol to an ether, we went from having something there to not. The same thing happens in amines when you take away its last hydrogen. So let's look at where these also show up here. So in the case of this example here, we have a primary amine, meaning you have two hydrogens on it. So we see two peaks. Notice they're still a little bit broad, but they're not as big or as broad as oxygens. Okay. We still have our regular alkane peaks here, and we have this peak right here. So we're right on the bridge. This is our carbon-nitrogen bond. Okay. But you can tell it's an amine by these peaks here. Okay. So let's move on to another functional group, okay? Aldehydes and ketones. And the key distinguisher between aldehydes and ketones is the fact that we have a carbonyl group, okay? So, and this carbonyl group is partially positive on this side, partially negative on this side, therefore it's very polar, and therefore it's very strong absorber, okay? So we see nothing up above except for our alkane hydrogens here. But notice we see a very strong peak. Carbonyl peaks are always strong. They're typically the strongest of anything in here. And they fall between the 1,700 to 1,800 range. Now it'll shift back and forth depending on what's attached to the carbonyl. So we'll see this move back and forth a little bit, going from aldehyde to a ketone to an ester. It's going to move around a little bit, but it's always going to be in this range. And again, it's because it's that carbon-oxygen double bond. And then there's nothing else. You know, these are all our single bonds down here. So this group right here is responsible for that strong peak there, and all the hydrogens are aliphatic. Okay, I told you that in an alcohol, it had a broad peak and it was up high near 3,300. However, in carboxylic acids, because they hydrogen bond and dimerize and trimerize, we get a very broad peak for the OH, but it dips down below 3,000. So notice this is where our sp3 hydrogens are. That OH dips down. So if you see it shift from being here to being down on top of your sp3 hydrogen, you should think carboxylic acid. To verify you have a carboxylic acid, though, you have to have your carbonyl peak there. And your carbonyl peak will show up in that range, and it should be very strong. So we can tell the difference between alkanes, alkenes, and alkynes because of where peaks show up. We can tell alcohols and ethers because of the carbon-oxygen bond with or without the hydrogen-oxygen bond. We can tell amines as primary, secondary, or tertiary between 2 peaks, 1 peak, and no peak in that high energy range. And now we can see carboxylic acids because it has a carbonyl plus a big, broad OH peak. So that's the great thing about this organic spectroscopy is you get instant analysis of functional groups. Okay. So let's take away that OH on that carboxylic acid and turn it into an ester. Okay. So what we see is this big, huge OH peak drops away. We no longer have it. And we still have our carbonyl peak here, but our carbonyl peak shifted a little bit higher. So it's closer to 1,800 than the regular carbonyl peak, but it's still there. And of course, we have only our single bond stretches down below that. So let's say you were doing a reaction in the lab and you started with a carboxylic acid and you made an ester. For example, our ester lab that comes up in a few days, you can actually take an IR before and after to prove that you have converted your carboxylic acid into an ester by just looking for the absence of the OH peak here and the shift of the carbonyl. Notice this carbonyl here is low, 1,700 to 1,725. In the ester, it's higher, 1,735 to 1,800. And that has everything to do with the idea that it no longer has that OH that can dimerize. It has a nice carbon-oxygen-carbon bond that shifts the energy up. Okay, so the amine equivalent of an ester is called an amide, right? And so just like before, we can tell how many things we have bonded to the nitrogen by seeing if we have something up here. So if we had a primary amide, which means we have 2 hydrogens on this, so this would be acid amide right here, we would actually see 2 peaks here. If we substituted it once with a methyl group, we'd have 1 peak there. Sorry, I hit the edge there. There we go. If we substituted one of these hydrogens with a methyl group, we would get just 1 peak here. But in this case, we actually have something with no hydrogens on nitrogen, and therefore we have nothing in that range, okay? But we do have a nice, strong carbonyl peak here. Now, notice that the carbonyl stretch is now lower than 1,700. Carboxylic acid was around 1,700. Ester was around 1,750. The amide is around 1,675. So even just looking at the carbonyl, we can tell the difference between an amide and an ester, because an ester would be up here, and the amide is down there, and the carboxylic acid would have the broad peak here. So it's very interesting to just follow that carbonyl peak as it walks around based on the electronic structure around it. Okay, So like I said, a secondary amide is one that has at least one hydrogen on there. And we get that one peak of the amine right here. And our carbonyl peak is still slightly below 1700 because it's still an amide. And if we replace that last one with a hydrogen, we get our two peaks that we were expecting for our hydrogens, 1 and hydrogen 2. And our peak is, again, below 1700. Our 1700 is right here. So it's still an amide, but now we know it has 2 hydrogens on it. All right, questions about that? So when you think about where peaks should be, think about the different types of bond in your functional group and think about where they might be. The light atom, heavy atoms above 3000. Carbonyls are going to be somewhere around 1600 to 1800. And it shifts around based on what it's done on. All right, and so that's the last I have for IR spectroscopy. These are the highlights here. What might be useful is to go ahead and write down your functional groups that you have, and then where you would expect to see a bond form, or where you'd expect to see an absorbance on. And what you'll find out is really quickly, if you fill out the table up here with the different functional groups, you'll start to see, ooh, I'm going to get 2 peaks in my IR. I'm going to get 3 peaks in my IR. I'm going to get 1 peak in my IR. Just by looking at the functional groups and what zones you might see a peak in. Okay, that's what I have for the first goal of spectroscopy. All right, I'm going to go ahead and stop recording. And if you have questions, go ahead and stay behind.